in this class we start with the complementary slackness theorem, which says if x star and y star are optimal solutions to primal and dual, and u star and v star are the values of the primal and dual slack variables at the optimum, then x star into v star plus y star into u star is equal to 0. We also mentioned in the previous class that since all x's x1, x2, y1, y2, u1, u2 and v1, v2 are greater than or equal to 0, xv plus yu or x star v star plus y star u star equal to 0 will become x1 v1 equal to 0, x2 v2 equal to 0, y1 u1 equal to 0 and y2 u2 equal to 0. We also know that u1 and u2 are the slack variables corresponding to the primal, and v1 and v2 are the slack variables corresponding to the dual. And there is a relationship between x and v, because x is the number of variables in the primal, which is equal to the number of constraints in the dual, and therefore the number of variables in the primal will be equal to the number of slack variables in the dual. Similarly, there is a connection between y and u, because u is the number of slack variables in the primal, which is equal to the number of constraints in the primal, and since the number of constraints in the primal is equal to the number of variables in the dual, there is a connection between y and u. We also verified the complementary slackness by considering this example, which maximizes 10x1 plus 9x2 subject to 3x1 plus 3x2 plus u1 equal to 21, 4x1 plus 3x2 plus u2 equal to 24. The dual is shown here, and we also said that in the optimum we said x1 is equal to 3, so complementary slackness says x1 equal to 3, v1 should be equal to 0. From the optimum solution to the dual, we realize that y1 equal to 2, y2 equal to 1. When we substitute in the first constraint, 3 into y1 plus 4 into y2 is equal to 10, therefore v1 is equal to 0. So we realize that x1 v1 is equal to 0. Similarly, from the optimum solution to the primal, x2 is 4. Now from the dual, when we substitute y1 equal to 2 and y2 equal to 1 in the second constraint, we get 6 plus 3 equal to 9, therefore v2 is equal to 0. So now we realize that x2 is 4, v2 is 0, so x2 v2 is 0. Similarly, from the primal, from the first constraint, when we substitute x1 equal to 3, x2 equal to 4, we get 3 into 3 9 plus 3 into 4 12, 9 plus 12 is equal to 21, therefore u1 is equal to 0. Now from the optimum solution to the dual, y1 is equal to 2, therefore y1 u1 is equal to 0. Similarly, from the second constraint of the primal, when we substitute x1 equal to 3 and x2 equal to 4, we get 4x1 plus 3x2 is equal to 24, therefore u2 is equal to 0, and we realize from the dual y2 is equal to 1, so y2 into u2 is equal to 0. Therefore the complementary slackness is satisfied. We also observe one more thing. We can also say that, for example, we take the primal and x1 is equal to 3, x2 equal to 4 is the solution. So when we substitute 3 and 4, the original constraint was 3x1 plus 3x2 less than or equal to 21. So when we substitute x1 equal to 3 and x2 equal to 4, we will get LHS equal to RHS, therefore u1 will be equal to 0. And when u1 is equal to 0, we realize y1 is in the solution. So another way of saying is, if the constraint is satisfied, the original inequality is satisfied as an equation, then the corresponding slack will be 0, and therefore the corresponding dual variable will be in the solution. Similarly, 4x1 plus 3x2 itself becomes 24. So, when the optimum solution to the primal satisfies one of the inequalities as an equation, then it means that the corresponding slack variable is 0, and when the corresponding slack variable is 0, the corresponding basic variable in the corresponding decision variable or variable in the dual will become basic. We can observe that from this example, in addition to understanding that the complementary slackness conditions have been satisfied. We will now move on to another example to understand little more aspects of the complementary slackness theorem and the usefulness of the complementary slackness theorem. So, we look at another linear programming problem, this time with 2 variables and 3 constraints. So, maximize 4x1 plus 3x2 subject to x1 plus 2x2 less than or equal to 7. x1 plus 2x2 is less than or equal to 7, and when we add the slack variable u1, it will become x1 plus 2x2 plus u1 equal to 7. Similarly, 3x1 plus x2 less than or equal to 11. So, we add another slack variable which is 3x1 plus x2 plus u2 equal to 11. Similarly, 4x1 plus 5x2 is less than or equal to 26, and when we add a slack variable it becomes plus u3 equal to 26, x1 x2 u1 u2 u3 greater than or equal to 0. Obviously, the contributions of u1, u2 and u3 to the objective function is also 0. Now, we now write the dual of this problem. Now, the primal has 2 variables excluding the slack variables. So, the dual will have 2 constraints. The primal has 3 constraints and the dual will have 3 variables excluding the slack variable. So, the dual is now written and then the slack variables are added to the dual. So, the dual is initially we will write the dual as a minimization problem. The primal has 2 variables without the slack variables. So, the dual will have 2 constraints and the primal has 3 constraints, therefore, the dual will have 3 variables. So, we will first write the dual with y1, y2, y3 and later we have added the slack variables. So, when we write it with y1, y2, y3, the dual will be to minimize 7y1 plus 11y2 plus 26y3, 7y1 plus 11y2 plus 26y3, which you find here y3, subject to y1 plus 3y2 plus 4y3 greater than or equal to 4. So, y1 plus 3y2 plus 4y3 greater than or equal to 4, and with the addition of a negative slack becomes minus v1 is equal to 4. The second constraint will be 2y1 plus y2 plus 5y3 greater than or equal to 3. So, 2y1 plus y2 plus 5y3 greater than or equal to 3, and with the addition of the negative slack minus v2 is equal to 3. Now, y1, y2, v1, v2, v3 greater than or equal to 0. v3 is also greater than, y1, y2, y3, there are 3 variables y1, y2, y3, v1, v2 are greater than or equal to 0. y3 is also greater than or equal to 0 and that has to be included. So, we have all the 5 variables greater than or equal to 0. So, this is how we will write the dual when we have unequal number of variables and constraints in the primal. And we also have to understand that when we first write the dual, we safely write treat the primal with the inequalities and then write the dual and then add sufficient slack variables to convert the dual constraints to equations. Now, what do we do with this primal and dual? So, let us do a few things. Now, let us first look at the primal and observe that we have a solution x1 equal to 3, x2 equal to 2 with objective function equal to 18 is feasible to the primal. So, let us verify that. So, x1 equal to 3, x2 equal to 2 is 3 plus 4 is equal to 7, feasible. 3 into 3 9 plus 2 equal to 11, feasible. 3 into 4 12 plus 2 into 5 10 22 is less than equal to 26 is also feasible. Now because plus u3 equal to 26 we will have u3 equal to 4. So this solution is feasible with objective function value equal to 18, 3 into 4 12 plus 2 into 3 6 is equal to 18. Now what do we do? Now let us look at the dual independently and then let us look at a solution y1 equal to 1, y2 equal to 1 as another solution. So if we look at this solution y1 equal to 1, y2 equal to 1 in isolation, we will go back and see that y1 plus 3y2 is 4, y3 is 0, so 4 v1 is also 0, therefore this constraint is satisfied. Similarly 2y1 plus y2, y3 is 0, v2 is 0, so equal to 3, this constraint is also satisfied. y1, y2, y3, v1, v2 greater than or equal to 0. y3, v1 and v2 are 0, therefore all the constraints including the non-negativity are satisfied. So this is independently another feasible solution to the dual. Now what is the value of the objective function for this? y1 equal to 1, y2 equal to 1 would give us 7 plus 11 which is equal to 18. So I have another feasible solution to the dual. I have a feasible solution to the primal, I have feasible solution to the dual. Therefore based on the optimality criterion theorem I can now say that both these are optimum to primal and dual respectively. So that is one way to understand primal dual relationship. Of course this does not have much to do with the complementary slackness. We will look at that again, we will apply complementary slackness and try to understand. The first thing is, if you are able to get a feasible solution to the primal, you are able to get another feasible solution to the dual, and if they happen to have the same value of the objective function, then based on the optimality criterion theorem both are optimum to primal and dual respectively. But then we will ask another question. It is not also that easy to get two feasible solutions independently, one each to the primal and dual having the same value of the objective function. So now we will apply complementary slackness and try to understand a few things. So let us go back to the same feasible solution here with x1 equal to 3, x2 equal to 2 and z equal to 18. Let us now not think of this solution y1 equal to 1, y2 equal to 1, let us not think of this solution. So now let us apply complementary slackness to this solution. So first let us define all the variables so that we can apply the complementary slackness. So when we apply the complementary slackness, x1 equal to 3, x2 equal to 2, we go back and substitute in the three equations now. So 3 plus 4 7 plus u1 is equal to 7, therefore u1 is equal to 0. 3 into 3 9 plus 2 is equal to 11, therefore u2 is equal to 0. Now 3 into 4 12 plus 5 into 2 10 is 22, therefore u3 is equal to 4. So this is the complete primal solution which also includes the non-basic variables as well as the slack variables. If we had actually solved this by the simplex algorithm, we would have got x1 equal to 3, x2 equal to 2 and u3 equal to 4. So we now have the solution to the primal and we now apply the complementary slackness conditions and see what happens to the dual. Now x1 is equal to 3, x1 is in the solution, x1 v1 should be equal to 0, therefore v1 should be 0. x2 is in the solution, x2 equal to 2, x2 v2 should be equal to 0, therefore v2 is equal to 0. Now u1 equal to 0, y1 u1 is 0, so it is possible that y1 is in the solution. u2 is 0, therefore it is possible that y2 is in the solution. u3 is equal to 4 implies y3 has to be equal to 0 because u3 y3 is 0. So now out of these 5 variables in the dual y1, y2, y3, v1, v2, we have now understood that V1, V2 and Y3 are 0, which means Y1 and Y2 have to be in the solution because the dual has two constraints. So let us go back and see what happens when we apply the complementary slackness conditions. So what I mentioned happens, because x1 is equal to 3, we will have V1 is equal to 0. Because x2 is equal to 2, we will have V2 is equal to 0. Because U3 equal to 4, we will also have Y3 is equal to 0. So let me write that here. So I will write Y3 is equal to 0. And because I have U1 equal to 0 and U2 equal to 0, so they have to, Y1 and Y2 can be in the solution, but since there are two equations, they are in the solution, and therefore it is now enough for me to solve this dual only for Y1 and Y2, which means I can leave out Y3, V1 and V2. It is enough to solve only for Y1 and Y2. So when I put Y1 plus 3Y2 equal to 4, 2Y1 plus Y2 equal to 3, I will get a solution. I just solve only for these two, Y1 plus 3Y2 equal to 4, 2Y1 plus Y2 equal to 3. So when I solve for this, when I multiply the first equation by 2, I will get 2Y1 plus 6Y2 is equal to 8, and I subtract 5Y2 is equal to 5, I will get Y2 equal to 1, and I will substitute to get Y1 equal to 1. So I get Y1 equal to 1, Y2 equal to 1. Now this solution Y1 equal to 1, Y2 equal to 1, V1, V2, Y3 equal to 0 is feasible and hence optimum. So now I am not applying the optimality criterion theorem, I have not evaluated the objective function of the dual. Now I say that I have a feasible solution to the primal, I apply complementary slackness and solve what I call as a corresponding dual solution, and if the corresponding dual solution is feasible, then it is optimum. It will also happen that the objective function value will be equal and will be 18, but I am not showing optimality based on the optimality criterion theorem, but I am showing optimality based on complementary slackness. So I have a feasible solution with z equal to 18, I apply the complementary slackness and evaluate a corresponding dual solution that happens to be feasible, and therefore it is optimum. Now let me look at another instance. Now let me go back to the same problem, to the primal, and let me take a solution x1 is equal to 11 by 3. So let me use x1 is equal to 11 by 3. From the second constraint I am writing x1 is equal to 11 by 3. So when I have x1 is equal to 11 by 3, automatically x2 is equal to 0 and u2 is equal to 0. You can see that x1 is equal to 11 by 3, x2 will be 0, u2 will be 0. Now I go back and substitute, when x1 is equal to 11 by 3, u1 will be 7 minus 11 by 3, which is 10 by 3. When I substitute here, 11 by 3 into 4 is 44 by 3, so 26 minus 44 by 3 is 34 by 3, 78 minus 44 is 34 by 3, and then objective function value is 44 by 3, 11 by 3 into 4. Now here I have a feasible solution to the primal. Now let me apply complementary slackness and see what happens. Now when I apply complementary slackness, x1 is in the solution, so x1 is in the solution, v1 is equal to 0, u1 is in the solution, y1 is equal to 0, u3 is in the solution, y3 is equal to 0. So that leaves me with v2 and y2 in the solution. So v2 and y2 are in the solution. So I will go back and say v2 and y2 are in the solution. So y1 is not in the solution, y2 is in the solution, y3 is not in the solution, v1 is not in the solution. So this will give me y2 is equal to 4 by 3. From here y2, 3y2 is equal to 4, so y2 is equal to 4 by 3. Then I go back and substitute. So So V2 is in the solution. So here I will have V2 is equal to minus 5 by 3, y1 will be 0. So here y1 will be 0. So y1 is 0 because u1 is in the solution. So y1 is 0, and I will have V2 is equal to minus 5 by 3 in the solution. And I have the same value of objective function, which is 44 by 3. Now I look at this dual solution and I realize that this dual solution is infeasible because V2 is equal to minus 5 by 3. So when I have a feasible solution to the primal that is not optimum, and if I apply complementary slackness and find a corresponding dual solution, I observe that the corresponding dual solution is infeasible, and therefore it is not. Only when the primal is optimum, if I apply complementary slackness, the corresponding dual after applying complementary slackness will be feasible, and both will be optimum to primal and dual respectively. Some more aspects of complementary slackness we will see in the next class.